A great pleasure to have Feras Dayoub from AIMA with us. So AIMA is the Australian Institute for Machine Learning. It's one of the premier places in Australia for AI. That's the University of Adelaide. So he's going to talk to us today about machine learning principles for XR-Driven Robotics. So it's a bit different from Wolfgang's presentation, more applied. We're talking about how you can use AI in robotics, a huge important area, and how that also relates to XR as well. So we've got about an hour. So it's not, after his talk, we may have a change in schedule. There was a woman from Google who was going to present, but she wants to present later. So she'll present at 1 o'clock. And maybe Richard will present if he's ready. Otherwise, we might push him later as well. But we've got some pizzas coming for lunch at 12 o'clock. So we've got some food countries soon. So I'll turn time over to us and listen up and ask questions as he's talking about. It's really interesting talk, I think.
Yeah, thank you very much, Mark. Thanks for the introduction. Okay, so yeah, I'm happy to be here. The talk is more about essentials for robotics, but what I did is I included the mention of XR and how XR might help. I'm not expert in using XR for robotics, so it will be more leaning toward robotics learning. And the talk will be really basics, machine learning, but with examples from robotics. So you might have heard a lot of what I said earlier, as mentioned, very quick, what is a neural network and what are the supervisors about. Here we'll go a little bit deeper, a little bit, not too much, because we don't have it. We're just one hour here. Before I start, I just want to know the audience. So how many of you have used machine learning, a deep neural network in your work? How many here trained a network? How many here collected their own data and labeled it and trained the network? Okay, one here. Okay, good. And two? Okay. Yeah, so when you're working with robotics, most of the time the data is custom and you have to collect yourself and you have to train your model because it's specific to particular tasks. So this is what makes this more applied compared to downloading a data set from the internet and train a model or use a pre-trained model. Just a summary of what a little bit of snapshot of what I do. My group in the transfer machine learning focus on robotic perception or computer vision, robotic vision for these robots. Over the years, I worked with a lot of these robots. Most of them were in the field. These two are free, were in projects with industry, where the code was running on the robot in an autonomous fashion, where the robot was doing one of the tasks designed to do. This one was on a Great Barrier Reef. This is one for weed detection and spraying. And this one for asset inspection. If you have a wall, you need to see if there's a cracks. Or there's an bridge you want to fix. It's extracted out. You can have this robot do the scanning. So what we will be talking about today. So I'll try to do it and stop some challenges when we are using machine learning for robotics, and I will say how XR help in this. Then we will go very quickly. The majority of the talk will be here, where we will go in one by one, and we will have an example, and we'll talk how these are used in robotics. And while I am talking here, I would like you to think how XR, how virtual reality, how mixed reality, how all of these can help. And I would like to hear how these technologies can help robotics be better. So as I look the challenges, you might say, oh, I have a way to make this better. If I use VR or MR, we will see. And then we will come to a conclusion and have some talk about future trends. So let me just make this so I can see what I am looking at. Okay, maybe this is better. Okay, so let's say there are robotics challenges here in this column, and they are the basic challenges. Robots always work in the real world, and in the real world, you can't predict what you will see, where the robot will go, and it's complex and unpredictable. Machine learning can help you if you collect a lot of data and you label them and you have a control of the robot and you have trials. You can create some policies or some control that will adapt and become better as you collect more data. But think about it a little bit here. It is almost impossible. We can't predict what the robot will see in the future. It's always changing, it's always novel situations. You see this in driverless cars. We hear that they are ready now, but from time to time we hear that they are in an accident because they thought that the right truck is the sky and they hit it, or they were confused with some scenery on the ground. So collecting data here is expensive and we need a lot of it. So VR, to have a simulation, we can generate almost unlimited level data as well, high quality data, and let the robot explore safely. In Tesla, currently, they collect a video of from the car taking maybe an intersection or going through around the corner. They take this video and they re-render it with people in it, with cars in it, interactive as well. So it is the same scene, but because they are using generative models, they put the car again in the same situation, but they make it more difficult and they collect more data from the same place. So this is not a simulated place in the sense that it's totally new. It is based on the video that we're collecting and they are creating new data. Data collection in robotics is slow and risky. This is the most hated activities they do student or a master student when we face in their studies when I ask them to go and collect some data because they have to drive the robot. They have to collect good data and then level it. For example, if you're an object detector, you want to test, you have to label what is correct and what is not. And it's a lot of hours. I have a student now working on a new data set. This data set to help researchers do change detection in a city scale. So imagine you have a city of Adelaide, and we want to detect changes over time. He spent 5 hours on every street in every major street in the city just to make the data, to label the data, what has changed, what has not. So this is very, very expensive. Usually what we do in robotics, and this is where what we call imitation learning or reinforcement learning, the idea of here is that we want the robot to collect its own data. So RL, which is trial and error, we let the robot go, and it hit the level that's a good data for a bad behavior, and if the good data go on and get to where it wants to go, this is a good example of a good data or a successful trial. But think about it. How many things can you break before you say no, this is not a good idea? We can't deploy this in a driverless car. We can't deploy this in a robot where people are around because a failed trial can be costly. So what you can do teleportation. Where you have the operator step in and do the trial in virtual reality. Okay, robot struggles to interpret ambiguous human intent. This is very, very, very important. Actually, it is both ways. The robot struggle to know what the human want to do, and also the human. If I give you a robot here, and this robot starts doing things, you sometimes look at it and say, "What is it doing? What is going there? There is no way to tell what the robot is doing." So here, maybe we can, in machine learning, we can sort of by having these models that can express what the human wants to do based on deep learning or maybe something like ChatGPT 4 or whatever. So there's something powerful that will tell us what the human do. In reality, we can use overlays. We can be explicit. We can just show what the robot is doing. We have the headset or we are receiving what information from the robot, or we are sending information to the robot, this can become more explicit and it's easy to communicate. An overlay that will tell where the human and the robot is sharing the same place, that will become easier to communicate. Safety and mixed workspace. We can learn, the machine learning allows you to learn these policies. You learn it, but you need to collect the data. You need to label them, and it is really expensive. In MR, you can add overlays as well. You can show the human where they should go, where they shouldn't, in overlay kind of a situation. So here, what you can see, notice the trend here is that this is enabling us to be more explicit in communicating between the human and the robot. Who knows what I mean by sim to real gap? Can you guess? Just guess.
Like a virtual simulator and we can set up already, and we can like test possible scenarios.
Yes.
So that we don't make mistakes in the real world.
Correct.
Yeah.
But why is the challenge? Why is describing it as a sim to real gap?
The simulator will still not be exactly one-to-one in the real world, and there will be challenges that we cannot actually simulate.
Even if the simulator is simulating this room exactly with all the chairs and all of us in it, when I train something in the simulator using rendered images, for example, when I take that model, that machine learning model, and put it on a real robot in the same room here, I will notice a drop in performance. The gap is real. So there's a very interesting paper where they did this, and they showed us that this is the model performance in the simulator. Model 1, Model 2, Model 3, they are here, and this is the same model. They are not retrained. They are the same model, deployed in the same environments, but on real data, and there's a gap. There's like 15% drop in performance in that data. So this is really this kind of I train things in sim and I take it to a real. I will still have a problem there. People are trying to solve it in using machine learning, what we call here domain randomization and fine tuning. So what you do here is that when you are training, you change the background. You start adding more variation in your simulation with the hope that now the model will start focus on what matters. So why this gap exists? Because the machine learning model now overfits to the simulated environment. Overfit to how the data is rendered in the simulator. So how do I solve this? I make this difficult to overfit. I change a lot of randomness, the background. I make the world big. I have very distracting images on the walls. But the task is still doing navigation. The world goes from A to B. But I wanted to focus on the task without thinking, without overfitting. So this is where people do this here. XR can bridge this gap, train in VR, validate with the overlay on the real world, and interact quickly. So here now I can mix this. I have an opportunity to mix reality with the simulator. So the input to the model is not just, it's not binary anymore. It's not just real images only or simulated images only. Maybe it's a mix. Because if I do an XR, I'm feeding the robot not just the images from the wall, but the overlays that have some kind of an extra information. This is
some people online are saying that this is hard time doing.
okay.
You might need to sit closer to your laptop maybe or
Okay.
sorry about that.
No, it's all right.
Which is
Yes. I will admit also people.
I've done that already. But
Yeah, thanks. Okay, so these are this where XR can help in robotics. Let's see. This is one of the NVIDIA. They love to sell you GPUs, and they love to find reasons for us to buy GPUs. And one of the reasons, if you are doing robotics, is that you can run their simulator, and so their simulators has a very nice physics engines. This means if a robot hits something heavy, it will feel like for the robot as if in reality, like if there's something heavy on the robot and the robot can't drag it around, the robot will not move. So this is Isaac. You can download, you can play with. I need the full. Need to speak just a minute. Let's try again.
As robots become more ubiquitous in industrial environments, it's essential that they can perceive rich 3D information about the world. In this video, we'll demonstrate how robotics can use
Yes, click on a real robot.
data space
Yeah.
to achieve a truly Instead of handcrafting multiple scenes, we can use Replicator, which is a part of NVIDIA Omniverse. Replicator makes it easy to procedurally generate a large number of environments. From a starting kit of individual assets, it uses a simple set of rules and constraints to fit your unique space and ensure that the testing and training results are representative of the real world. Now that we have a simulated environment, let's see how we can help the robot navigate through it. First, the robot needs to know where it is in the world. We compute the robot's location and movement from images by tracking visual features in the surrounding space. NVIDIA Isaac Ross Visual SLAM taps into the power of the GPU to bring these algorithms to any robot equipped with an NVIDIA Jetson module. But knowledge of the robot's position alone isn't enough to safely navigate complex industrial investments. Robots must also be able to discover obstacles and obstructions on their own. NV Blocks, also released as part of Isaac Ross, uses RGBD data to create a dense 3D representation of the robot's environment. This includes unforeseen obstacles that could cause a danger to the robot if not observed in real time. Here, we show the onboard reconstruction matched against the real geometry of the simulated scene. We obtain an accurate mesh while still being able to run real time on a Jetson. In this dense 3D representation, we compute traversable zones in which the robot can safely move. In this example, collision costs are used as inputs to an open source code, Rock2Nav2. This enables safe navigation through the warehouse. With Isaac SLAM Replicator, Isaac Ross Visual SLAM, or Isaac Ross NV Blocks, you can more easily bring the power of simulation and visual navigation to your robot today. As robots become more ubiquitous,
Okay, so what we saw now is the power of simulators, where you can replicate the world and you can write code on the robot that has sensors that look like the real sensors. What I want this point to get to land in your mind, because this is very powerful. The same code you write here for this robot, the same code you copy and you put it on the real robot, it should work. There's no difference between the system that's running this robot here and the real robot that is that robot, because that robot is modeled based on a real robot you can't buy. So this means that accessibility to program robots now is much easier to access, because you can now go home if you have a good GPU, get this running, and start learning how to program a robot. And you can use all of this path planning and the algorithms of the chart. They exist. There's no need to rewrite them. And you run your application there. And then you can, if you have a robot, you can take it and deploy it. We need to zero. Okay. So now we will go more into so yes. Yeah, this is multitasking. Okay, so now we will go into a little bit deeper in the presentation. I think I have. I didn't start the timer, so I'm not sure how much time I have. I think I have. I have 5 minutes. Okay, so I will be talking about machine learning concepts, but with examples. With examples from let me just unmute here. Yeah. Good examples from robotics. So we'll talk about supervised learning. I think we heard about this in the lecture before me, and maybe earlier yesterday as well. We'll talk about deep learning and neural network. I will give a little bit of more explanation for transformers and attentions, because this is now the state of the art, or the most successful. I will have some comments about RL, which is reinforcement learning, and how XR can help. I mean, by now, you might guess why we need machine learning in robotics. I want to take the information coming from a sensor on the robot, similar to us human. Our brain will taking this information from our eyes and converting that to actions. For example, if I want to grasp or get the cup, my brain is getting information where the cup is, where my hand is, and this is translated to this action that enables me to do what I intend to do. So machine learning in the context of robotics, think about it like this. It's a mapping, it's a function that you input sensor data in, and the output is the action the robot needs to take. And the machine learning model is in the middle that is giving you this ability. So it's also we want these models to be able to handle uncertain environment as well. And we want to enable the robot to learn policies by maybe learning from a demonstration or behavioral cloning. So what is supervised learning? We might have heard this definition multiple times, but in the context of robotics, it's the learning to map the input, camera images, for example, to output maybe object labels, or maybe this 3D bounding boxes in the 2D image you can see here. Again, this model you can download and run. It is available. It's from NVIDIA, I think. Learning to perceive, we want to just enable robots to perceive and to imitate. And this is a much harder problem in robotics. This is what we call behavioral cloning. It's much harder in robotics. It's very easy to implement currently. In PyTorch, who used PyTorch before? Who know what PyTorch is? Okay, but not a lot. So PyTorch now is a Python library, a Python framework, where you can go in and you can say import object detector. And now you have an object detector. You say you instantiate in Python the object detector, and you point it at the webcam you have, and now you have an object detector detecting whatever they trained it on. So this is the accessibility of these tools are really now very easy. You can get very strong performance with good data, and it's most of the time this kind of supervised learning is what we do at the beginning of any deployment. We ask ourselves, can I collect data and label it and then do supervised learning to solve it? If yes, do it. If no, now things become more difficult. Now we need to think deeper in how we solve the problem. Now you heard about the neural network, and this is it's not a new algorithm. It's not a new thing. This shallow network which has input and then a hidden layer and output. It was I think in the I can't remember 60s, 70s. I will be mistaken, but it's old. It's not a new idea. But at that time, when they invented and started playing with this, it was very promising, and people got very hyped about it. But at that time, there was not a lot of data as available now. One, two, the hardware, the compute, the GPUs were not as strong as today. So we didn't think about it until 2012, where we have something in computer vision called ImageNet Challenge. Do you know who knows what ImageNet Challenge is? Or in research, to make things move forward, we create challenges. Maybe in XR, in your field or the field you are entering, you might have a lot of these challenges in conferences where you try to write a paper to beat everybody else in that particular challenge. At that time, they have something called the ImageNet Challenge, which is a data set for object recognition, which has 1,000 classes. That's huge. 1,000 classes. So I give you an image and you want to tell me out of 1,000, which one is the one in the image. People were struggling. There was doing a lot of this techniques before deep learning. And in 2012, AlexNet came on the scene. Alex is the researcher who created AlexNet. He used convolutional neural network, again from the past. It's not idea he invented, but in his bedroom or his garage, I think, he has access to powerful NVIDIA GPUs. And it let it train for a few days, I think a week. And he came with the result that's, I think, 15% better than everybody else. At that time, people in computer vision start thinking, are we done? Should we stop doing research? This is crazy because every year it was 0.5% better, 1% better, 0.5% better than the last years. And suddenly this guy come in and won the challenge using supervised learning because he used deep neural network, neural layers, and used convolutional. I will talk about this now later. And he got very good performance. Since 2012, things are moving toward deep learning in a fast way. So deep learning is neural layers. Of course, it's expensive to train. It needs a lot of time. And if we talk about the architecture we use mostly in robotics, or what we still use the small feed-forward networks. We also use CNN, convolutional neural networks. We use RNN and LSTM as well, and we use transformers. Or they are still used, and they have each one of them has their own kind of benefit. So if we want to go a little bit into the math, you remember the function I talked about, where you have an input here and the output. The output is something you want, the action here, and the input is maybe the sensory data in our case. Let's assume I have this three distance sensors, and it's giving me distance to things around me. Let's assume it is this way, and this way. And it's giving me one scalar for each one of these, and how far things around me. So this is the sensor readings here. And so this means R3. This is X, you feed it to the input. This is the input to the neural network. Y might be the actions, might be go left, go right, maybe stop. So this is mapping the sensor to the action. Again, this is what supervised learning here. And the model, the weights of in the neural network is this matrix of weights and biases. And we are literally doing matrix vector multiplication. And the whole training is about finding the best weights that if I give it 0, 0, 1, it will tell me go left. It will give me 0, 0, 1. If 0 is right, 0 is the second 0 is go straight, and the last 0 is go left. This is the output. And the input is the sensors, which is how things are far from me. So if I have things here, I want to go this way. So this is what we want to learn. And in the middle, it's not just linear kind of multiplication of matrix and vector. We wrap it with non-linearity. So just to make things more interesting. But it's not that complex. It is this matrix multiplied by this vector. We add the biases, and we pass it through non-linearity here, just to make the decision boundaries more complex. And this is the hidden layer. We take everything we got from the hidden layer, we repeat with a new matrix, a new bias, and we get output. That's all of it in terms of what's happening under the hood for the deep neural net, and for this small neural network. The non-linearity here, there's a huge variety of them. The best one so far is learning. A lot of people use it. This means simply what's said, if the input is lower than 0, make it 0. If it is positive, greater than 0, keep it as it is. That's the non-linearity we have here. Of course, in math, there's a lot of foundation and rigor in why this works. But for you as an end user, it's very straightforward. It's not complex math. So here we have we put the sensors in this vector. We have the data which we moved it. We collected this data and we use this for training the neural network. So in this case, the input will be 3. For example, we decide we want, and the output, as I mentioned, is 3. The matrix to make the math work need to be 5 by 3, and we have 1 bias. It needs to be, sorry, it has 5 biases, and it needs to be, for the second layer, it needs to be 3 by 5, and my bias is 3 at the end, because I have 3 output. So this is meaning I want, for this problem, I want to train 38 parameters. Why this number is important, you will know later. But remember, for this small problem, where I have a little number with the 3 sensors and 3 options what to do next, I need to train 38 parameters. The more parameters you have to train, the more memory in the GPU you need, the more data you need, the more time you need. So this one is very simple to train. I collect the data like this is because of what I collect and what I want the network to give me answer. This is the correct answer. You can do it to representation, but in this case, you might decide to do it in virtual reality. For example, you collect the data and you treat the robot there. That's possible, but you need to collect data that is similar to what the robot will see in reality. That's the condition here. You can't make the robot fly if it doesn't fly in the reality. Or you can do this manual labeling. A lot of people do this manual labeling as a step after collecting data to clean, because these networks are really sensitive to the data you give it. It's data-driven approach. You decide on your loss function. I choose cross-entropy loss function. The loss function is the way you are training these parameters. So think about training a neural network is you take some of the training data, you feed the input to the network, you get the answer, you compare the answer with what it's supposed to be. There is error. This error is used to change the weights in the matrices. Remember that we have 2 big matrices in this network. And these are numbers. So either I want to increase this number or lower this number, but how do I do it? I do it in a way that's informed by the error. If the error is big, I will move this a lot. If the error is small, this is not working. I don't need to move them a lot. I need them slow. And this function will calculate the error. That's all you want to learn here in loss function. And there's a lot of them. We will invent them. But this one, there's few of them are established now. One of them is this. You will hear this gradient descent. Gradient descent is the way we change the numbers in the matrices, and it's based on the direction that minimizes the error. Like, if I say to you that you decided to go left, but you went too much left, I calculate how much error you did, and I need to find the direction. Do I do this or do I correct more left? Like this is where the gradient idea here, and this is the numbers in the matrix. You see that theta is the matrix, and what we are doing is subtracting amount from it based on the error. And exactly what I'm saying here is that I find it, and then I decide how much I want to break this, to tune these numbers based on this error in a direction that reduces the error. The training group, it's now very standard. I have these matrices, 38 numbers, remember? I fill the numbers randomly at the beginning. And then I start feeding it data from the data I collected. I compare with the correct answer. I have the error. I calculate the error here. And then what we call is back propagation. I go backwards in this network using the direction of the error, and I adjust the 38 parameters in the networks. I do this in epochs. In multiple times, I go over the network. Then I get some training curve. These are how good the network is getting over time. And at the beginning, you expect it to be really bad because the 38 numbers we selected for our matrices were random. So you have to, and you want to what you pray for is that this is go down as we go into the epochs. As we feed the same data again and again to the network, we are updating this we are updating this we are getting the error, and we are seeing going down as we go. So after you train, we need something to judge this network, and you hear about accuracy. So accuracy here is the number of corrected predictions on everything you tested. Like for example, if I collected 100 steps, and in 80 of them, the robot followed the correct action. If it's supposed to go right, it went right. Then my accuracy is 80%. This is one of them. But the problem with this accuracy is that if you have a binary problem, for example, let's say I have a driverless car, and I want to detect kangaroos. I don't want to hit kangaroos in Australia. I'm going in the car, and the model is saying there's a kangaroo or there's no kangaroo. Okay? Let's assume I said 1,000 images, and the kangaroo appeared in 5 of them, and my model didn't detect any kangaroos. How much is the accuracy? How many times did the model get it right? 95%? Yes, it got it 95% because it says there's no kangaroo and there was no kangaroo. But say no kangaroo. Let's repeat the example. 1,000 images, and the job is for this model to detect if there's a kangaroo or not. This model always says there's no kangaroo. The kangaroo appeared 5 times, and we missed it. I want to calculate the accuracy. The accuracy is almost 100%. No, because it's correctly saying there's no kangaroo. But this is the accuracy. The accuracy is how much correctly you detected. Yes. Correct. So this is exactly what I'm trying to say. Accuracy, if you just use it without thinking, it's might be it's not the correct method to use. If there is imbalance in the classes in the problem, you should not use accuracy. There's different things. There's precision, there's request, there's scopes, and so on. Okay, so this is what this is here the concept or the terms: true positive, true negative, false positive, false negative. And you hear them in the news sometimes when they talk about tests, vaccine, they talk about multiple things that's going on to that thing. So it's important for you, even if you are not machine learning expert, to get a sense what a true positive is, what a true negative is, what a false positive is, and what a false negative is. So true positive, I'm trying to detect if the disease exists, is present in the person, and I was able to do that. So true positive. True negative, the disease does not exist in the patient, and I'm saying it doesn't exist. That's true negative. False positive, I'm saying there's a disease in this patient, but there's no. So I'm falsely saying that there's a positive. False negative is there's a disease, but I'm saying there's no disease. False negative. So this it takes a little bit of time for you to get your head around. But what I'm mentioning this is in robotics, depending on the application. In robotics, depending on the application, this might have different way or importance. For example, if let's go back to the robot where trying to detect weeds. Weeds, you need to spray all the weeds in the field, because if you leave some weeds, they will come back very quickly, and that's a very waste of time because they need to spray again. Which one is most important? Which one is more consequential if you get it wrong? False positive or false negative? False negative. Yeah, false negative. Close. Yeah, so you are predicting there's no read, but there is, so you missed it, and now you have to spray again. So in this example, false negative is more important. What is the second example? What's consequential if you get it wrong? Yeah, false negative. You will hit. False positive will be annoying because false positive every 5 minutes. Oh, there's no. So that's where it's very annoying. Okay, so now the question I say is why we need to move away from, or why not just stick to this feed-forward networks? They can't scale. This is the problem. The problem is the input is not just 3 sensors. We have sometimes, or we feed these networks images. And the image, if it is 100 by 100, these are a lot of pixels need to be entered, and each one of them has its their input. So this does not scale. So we need something better. And this is where we go for convolutional neural network. So convolutional neural network, here the trick is to do what we call filter, and the filter will go over the image. So the filter is the W, the matrix with the weights. And I want to learn that, but I am moving it over the space. It's a less weight than the feed-forward neural network. I have a lot of other lines which enable me to lower the amount of parameters I need to learn. They call them and I can be fully connected, similar to what we saw in the Blitz example at the end. So if you look like this, the image becomes an input. I have my kernels that go over this image and create what we call feature maps. I use this subsampling. Just move this here. Can I just do this? No. Okay, so yeah, and I'm going lower until I get to this fully connected and I have my output. So now instead of figuring 3 sensors, I can figure an image of what the robot see, and I will ask it to decide go left, go right, or go straight. Convolutional neural network will allow me to do it. So the math for the convolution is not a new operator. It exists in computer vision for a very long time. But there are number of parameters now. If I am using fully connected neural network, is 1 million parameter. But if I'm using convolutional with this configuration, I'm down to 1,200 only. So this is with the power of convolutional neural network. You understand this point? Because I have the convolution, the number of parameters I need to, let's step one step back. If I want to take that example, about finding the right direction, but I'm feeding it an image, and the image is 64 by 64. Do I mention it here? Yeah, I'm mentioning, let's assume 64 by 64 with 3 channels. That network, that symbol network will become, instead of 38, it will become 1 million. That's too big. But if I'm using convolution, it becomes 1,200. Now more manageable and easy to use. I need to speed up a little bit. This is how the neural network looks like. When you are using bytecode, you can just really put these layers one over each other. Very simple. I think I put it here. So this is the full network to detect a red cube. You can do it, and you can collect the data by yourself and label it and train it. It's a fun exercise, especially if you have access to a virtual environment, or you have a simulation. You can do this. You don't need a robot, because if it's a red cube detector, it doesn't need a robot. It can be for other applications. Data collections, I would say you can use ISAP sim, but there's data for common objects. I don't want to No need to go here. Okay, this is more about the variety metric. I mentioned accuracy and it has some shortcomings. We can use precision, which is true positive over true positive plus false positive. We can use recall. We can do F1 score and the area under the curve. Each one of these will have a different meaning and purpose. You can use them to judge the network, and depending on which one will be much more important than precision in your application. Okay, this is what we call the receptive field in the convolutional neural network. When we start in the neural network, when you input an image, the first layers are looking for edges and lines and corners. As you go deeper, these become combined with each other. And you get more complex. Now you can see a box or you can see an airplane, but deeper in the network. As you go deeper, things become described in a vector space in a much more abstract way. So you can now have a more rich summary of the image. But we start from the edges and the corners. So these are the receptive fields that the convolutional neural will see. At the beginning, we only see a few pixels. But as we go deeper, the kernel will start handling all the space, all the input space, but later. So that's the core idea of this receptive field. Why we need to move beyond CNN? In robotics, we're always dealing with sensors are coming in terms of frames or readings from the sensors. In your case, if you have an avatar in the game or in the virtual reality, it's seeing things and things are moving. So things are, there's time here, and I need to produce things based on the happened. I need the context of what happened so far. So we move from CNN to what we call recurrent neural network. The idea here is that every input will get with it an encoded history. So let's assume how do I explain this? Let's assume I am trying to draw something, a frame. Before I do this frame, I look at all the frames I draw so far very quickly, because that will influence what frame I will there's a continuity. So what's happening here is that we are bringing the state from the previous step and feeding it with the current input. This is what I want you to understand, that this is taking the history with it, but it's not taking the last step. It's taking a summary of the history. It's taking a summary of the history with it. So this is the RNN. Can you recognize here the vector, which is a matrix by a vector, and a pass. The same thing, what we saw in the feed-forward neuron. And this is the nonlinearity in this context. But this is what's happening here. Before we only saw the X, N, and the pass, but now we're seeing H, T minus 1, which is the history from the previous step. That history is not only the last step, it is a summary of all what happened so far. I don't want to, so this is the high-touch code for this network, and it's very easy to implement. But why we don't stop there? Why not just, okay, we have a feed-forward network. It doesn't scale when the input is like images or high-dimensional. We go to convolutional neural networks, but convolutional neural network doesn't handle time, so we go to RNN. But why we need to move beyond RNN? Why have a new architecture? That's or give us memory, the history, but they are slow, hard to train, struggle with long-term dependency. If your history is long, and if something happened earlier in the history, matter, sometimes it doesn't matter. But if in some applications, if it matters and this history needs to be kept, these networks will struggle. And now we come to transformers. Who heard of transformers? Only 2, 3, 4, 5, 6, 7. Very good. Transformers is like a breakthrough in our lifetime. CNN was a breakthrough, the convolutional neural network in 2012. Remember the AlexNet and the Alex story when in his garage? This one here, a group from DeepMind, I think, from Google, came and say attention is all you need. That's the title of their book, and they introduced what we call the transformers. This is coming from natural language processing, and it's coming to solve what RNN can't solve. This allows us to process all the input in parallel. So if I have a history, I can keep the sequence, and every time I take it with me and feed it to the transformer. So it's allowing me to I can process faster, and also it can handle long dependency much better than RNN. So this is where it's one step above RNN, but also it has something called attention. Let me just go here. Okay, let's go some example. This is the best way to do this example. In robotics, they opened like they opened possibilities which were only possible in science fiction, which is I can talk to my robot, I can tell the robot the task I want, where the robot didn't do this task before, and it will execute it. Using a neural network end-to-end, meaning there's no small components I wrote to do this task and this task. So I can say to the robot, pick up the red cube, and I give it an image of a table with red cube, blue ball, and green cylinder. So this instruction and the image are the input. So how do we do that? We take the image and we detect the object in it, and then we use convolutional neural to the last layer. Remember, the last layer is the very high semantic summary of the input. We started with edges and start states, but we end up with something that describes a red cube, blue form, and we say that which will look a long view vector of a lot of random numbers. They're not random, but for us, we can understand what this 0.5 is talking about. Maybe it's talking about the size of the cube or the color or whatever. This is where it's difficult to understand what these networks are doing. Now I have a vector representing the first object, vector representing the second object, vector representing the third object, and I take my instructions and I converted it also to vectors, to multiple vectors. So the magic here is that for this transformer, it doesn't matter if you are inputting images or language, because at the end of the day, all of them are encoded in this one-dimensional vectors. Think about it. Now I can input audio. I can input 3D point clouds if I can convert it to a list of this vector. This is really very good. And then I can also input these instructions. I can tell it that whatever will come after this special instructions is representing an object, and whatever come after this is what the action, which is I will treat the action here in this example. Remember from the last lecture, before this lecture, the lecturer was saying that it's about it complete the sentence. You give it a sentence and you say it can predict the next word in the sentence. In this example, we will give it the images and the instructions, all of this as a sentence, and we want it to complete what is the action need to be taken. So the completion here is not another word in the sentence, it is what's the action need to be taken for this or go left or go right or grasp or so on. So this is how of a sentence is similar to using it in robotics. So now there's a lot of details. I don't think I have time to go into, but we have something called position encoding. RNN is taking time step by time step as an input. So input, and then you bring the history with you. But here we are taking all the sequence at once. We need to tell the transformer what comes next, what comes first, what comes second, what comes third. This is what we call position encoding. It's more complex than this, but this is the simplest way to think about it. And we do this encoder step, and we get to the attention. Okay, I will spend a little bit of time explaining what attention is for somebody who have zero machine learning background, because the concept is really interesting. You don't need a machine learning background to appreciate what's happening here in this video. Imagine I want you to complete a sentence, and I give you the word in the sentence. For example, the red cube on the moon. There's a red cube on the moon, blah, 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 and we need to change to complete the sentence. We started by each of these words has a generic vector that represented it. So let's say the word I can represent this in a very there's one way to represent it to start with, which is the vector that does that. And I have the red cube. Each one of these I'm bringing from something pre-computed, and it's represent the word in general. Okay. Attention allow these vectors to attend to each other and change their content. So this vector that I started with become more relevant to the sentence. Now the cube on the moon, the location of the cube now is a more interesting part. It's not like a red cube on the table. The moon bar will influence inside this one-dimensional vector the information about the position of this cube. It will become more interesting. Attention will be more, because that's the most interesting part, that it is on the moon. So here, now exit an attention module. I enter the attention module with this vector, which represents red cube in general, the moon in general, that is very general. They go into each other, a new set of vectors. Now the attention inside this vectors has shifted. The things that's not important become higher or increase in value, in value, and the things that is not relevant become lower. That's very important, because whatever will be the output now is more relevant to the sentence. So that's in summary what attention is in this. And this one is the equation they came up with. I don't think we have time to, but I can really spend a semester explaining attention in details. But the way I explained it, I hope it will give you a sense of what I mean by that. Okay, the decoder in transformers is it has something called cross attention. This means what I want to generate is an action, but the input is images and sentences. So there's a cross here, because they are not the same kind. Similarly, think about this as translating between English and French. The input in the encoder here is the English sentence, and what I want from the decoder is to give them the French translation. But I want the French translation to be related to the input. So this is where we have here something called cross attention between the encoder and decoder. This is very high level. Not worry if you don't understand the details, but if somebody mentioned encoder of a transformer and decoder, this can if this come to your mind, that will give you some starting point. Okay, so that's all about the transformers, but how do we train them? People love to train them now using behavioral cloning. This means a person controlling two arms and doing the task we want the robot to do. Now you can think, okay, how do I do this in virtual reality? You can, as long as you can collect the data that represent reality and translate. You can also do this with a headset if you want. Maybe you want the person to hold anything. You can just move things in the environment, in the virtual environment, and you have a robot that is copying what's happening, and you are collecting data from there. So this is what we do for training. Very expensive, $10 million to train one model for one of Google models, the robotics. They show you this impressive demos, but behind the scene there's a very year of collecting data and millions of time spent on people doing this, because we need a lot of data, supervised learning or data-driven machine learning is expensive. I think you heard about reinforcement learning. This is another kind, which we generate our own data by trial and error. In robotics, RL by itself is difficult to make work because we need thousands and thousands of trials and errors, and it's not possible for wear and tear and safety and all of that. So we need to do it in, we need to find an easier way to do it, and this is where we do simulation, and we collect data. It's cheaper, but you still have the reality or the sim to real gap. Some people, this is a new trend and it's very interesting. Maybe it will translate to something outside robotics. What they do is they train a model in the virtual environment, and we only deploy the model in the virtual environment. So the model will never see real data. The model is controlling something in the virtual environment. And there's a real thing outside the virtual environment, a real robot, which is job is to copy whatever the virtual instance is doing. Can you think? Do you see the difference? Can you catch the difference? The first scenario everybody was doing before, I go to the virtual environment, I train my model, and then I take that model and put it on a real robot and start giving it real images or real sensor data or real audio. And then I will get frustrated because it's not working as good as the virtual. But if you have a very powerful compute and access to cloud computing, you go to the virtual environment, you train there, you leave the group, you use the virtual environment, and you have a very high connection to a real thing that is not doing any intelligent thing. It's just copying whatever the virtual entity is doing. Now you can think about how would that work? It can work, but if I am in the virtual environment and I move this like this, my clone should do and move the chair in the same way. But in the virtual environment, this was like this, and in the reality, the chair is like this. That happens very quickly. So you need the virtual reality to upgrade very quickly, to copy the reality very quickly. Require a lot of sensors, but if you can solve that, and you are always having an up-to-date virtual reality, that can be solved. There's too much detail. This is about the implementation of IO and how XR can help. But I think I should wrap up. Now I'm out of. So for that, I will do this final slide, which is the conclusion. XR solve data and safety bottlenecks, while machine learning provide adaptable intelligence. This is good. Simulation first, then AR or AMR validation will create a robust sim to real pipeline. This is crucial. This pipeline from sim to real, and human in the loop via reality, post transparency and trust. Because if I have overlays, I understand what the robot is doing. The robot understands what I am doing. Emerging trends. Foundation policy trained on billion of XR services people are using in virtual reality or XR. If I have a very good simulator in cloud, I can do edge rendering and low latency. This is crucial. Multi-human teleportation as well. I can ask cloud source in the VR. That's I don't, as I said, I don't have experience in this field, but for me this sounds very exciting and a lot of problems to solve. Technology and push for mixed reality safety visualization standards. I guess you have this in your field. How to benchmark XR-generated data quality, because at the end of the day, we want it to work on real. How do we certify mixed reality safety layers? And we balance on-device with client inference. This is crucial. Google latest model is all on-device. Imagine ChatGPT working on a small robot with the same intelligence. That's crazy, but we can't do it now. It's too expensive, and we need the cloud. And the privacy and immersive, when we are collecting data using the sensors, you still need to answer for the privacy. Okay, that's the last slide. Thank you for listening. Happy to answer any questions.
Thank you for your presentation, Feras. Does anyone have any questions in the room or on Zoom? Anyone?
Can I sorry.
Yeah.
Can I ask for the XR for the adaptability? Is there any other methods that you can combine with RL, or using RL is sufficient?
Yeah, so this is will take us here for the limitation of our. So I think XR can help in high fidelity simulation because I want the robot to do the trial and errors, but I still need the simulation to be very high fidelity, and that's expensive in this scenario. The XR can allow intervention during the trial. So maybe you are with the robot during the trial and allowing to change things. But when you are in, we run these trials in simulation without rendering, so it's very fast. But as soon as you get the human in, that will slow things. So maybe there's a research questions about how you can intervene. Maybe the robot will ask the human for some input. That's where XR so allow you to get in much easier and understand what the trial is doing, what the robot is doing. In RL, the biggest problem is the reward function. So the best reward function, I think, is the dense reward function. If the action the robot do, there's a signal back that's is it getting you closer to the end goal or further. But in robotics, most of our reward function is sparse. So maybe VR or XR can help with dense reward functions. So that will make the training much better. You have more observability of the environment and so on. Yeah, there's a randomization as well. The gap, it allows us to randomize. Yeah, I think there's a potential here, but there's a lot of research to be done in terms of this integration.
Any more questions? Maybe one or two more. Online or offline? Well, I guess I have a question. Can a robot train another robot and then just replicate that infinitely?
So the answer here is if the first robot is training the second robot, why not just copy the same model? Why need because there's no maybe this is an interesting problem. So let's assume I have two robots with vastly different capabilities. I have one robot with higher capabilities, better sensors, better actuators, and then I want to distill knowledge from that robot to a smaller robot. Maybe that works. I haven't seen something like that in embodied kind of training, but we have something called model distillation and semi-supervised learning, where we have a teacher and a student models. We do this for object detection, for example, or classification. But physical robot training other physical robot, I haven't seen before. There might be case for that, but interesting case.
Because it's a potential that the error may stack up if that happens.
Yeah.
Any questions from the audience? Maybe one last question from my side.
Yeah, sure.
So, some of us, including myself, have seen a really cool video from Boston Dynamics,
yes,
right? Where they navigate difficult terrains. So, any insights you can share about developing a robot model like this? Is it based on, for example, like how you share the methods where someone wears sensors and walk across terrain with this plane or like that?
Yes.
Or is it done through VR and essentially this sort of very high level bipedal robots?
So there's two different kind of demos you saw in live. The Boston Dynamics and this Atlas, where it's doing a lot of this movement. This is purely so they have a very accurate representation of the 3D structure in front of the robot, and the robot motion is really very tracked and very precise. They are showing us what the control can do without using cameras. They are not using perception. There's no intelligent decisions happening in that move. It's purely the execution of the steps. That's impressive, But that's not the whole story. Now we have the flip side where we have, for example, DeepMind or Google selling us a robot arm trying to open a box. That's mainly based on behavioral cloning, demonstration from many data collected from people doing this using the same arms but control. So that's two different kind of videos. Currently, these models can do some impressive tasks, but they fail very quickly. They can't fail if the thing is novel. We've seen it in the training data, but we are getting really close to a very capable kind of a humanoid robot that can clean your house. We might do this in 5 years.
Okay. Yeah. Thanks so much.
Thanks.